Hi everybody, I'm Murray Barnes, the lead developer of VPLanet. In this video, I'm going to describe the structure and rules of input files so you can perform your own VPLanet simulations. Before we begin though, I need to define a few terms that we use to describe various aspects of running VPLanet. First is that VPLanet accepts a single primary input file, which is the file that you would include on the command line. This file provides the top-level instructions for VPLanet. The primary input file contains options, which provide instructions to VPLanet on how to set up and perform an integration. Each option accepts one or more arguments, which are the specific values you selected for that option. One of the options in the primary input file accepts a list of body files, which contain options that describe each object. So the primary input file tells VPLanet which objects are part of the system to be studied. Collectively, the primary input file and body files are called the in files. The body files also contain outputs, which are the parameters that will be printed to the forward files or the backward files. These two files contain the results of the simulation over time. In other words, the time series data of the body's parameters. In addition, VPLanet can also write a log file that contains the initial and final conditions of the simulation. So let's now take a look at an example primary file in detail. In this case, we're looking at a system that consists solely of the Sun and Venus, and we're going to simulate Venus's water loss for about 4.5 billion years. So let's take a look at each of this file's components. Okay, here's just the first line. You can see that it begins with the pound or hashtag sign. This symbol tells VPLanet that all text after it on that line is a comment and should be ignored. All whitespace is also ignored, so you can have as many blank lines as you want in between options. Now here are the next few lines in the input file. The first actual option is sinput, system name, which is a required option and is just an identifier for this simulation. iverbose is the next option, and it sets the amount of text VPLanet prints to the screen. 0 is no text, 5 is all text. boverwrite disables or enables the overwriting of previous results in the directory. Next, sa_bodyfiles is the list of all bodies to be included in the simulation. Note that the option name must be the first string on the line, and exact spelling and case are required. You may have also noted that each of these options contains a leading lowercase letter. These characters denote the type of argument the option accepts. So B means the argument is a Boolean, and the argument must be either 0 or 1. I is an integer, so the argument must be a whole number. D stands for double precision, so that means the argument can have decimal places. S stands for string, meaning non-numeric characters are allowed. If that leading letter is also followed by a lowercase a, then the argument can be an array of values. In other words, more than one argument is allowed. So in the lines above, we see that sa_bodyfiles has 3 arguments: sun.in, the $sign, and venus.in. That $sign is a special character that tells VPLanet to continue on to the next line to obtain the next argument. Note that the $sign and hashtag symbols are the only special characters in VPLanet input files. All right, let's check out the next block of text in the input file, which are the units for the input files. The units of the arguments in VPLanet's input files are customizable. So if you include lines like these, then, for example, VPLanet will assume that any option that represents mass will have an argument whose units are solar masses. The units can be set for each body file individually, or if these options are set in the primary input file, then all bodies will use those same units. However, you can still include units in a body file, which will then supersede the values in the primary input file. The available unit arguments are presented in the documentation and are available in the onboard help. All right, let's check out the next few lines. VPLanet can write out a log file, which is optional, but we do recommend it. Note, however, that the units of the outputs in the log file are in system units, by which I mean the units of the actual calculations inside VPLanet during an integration. VPLanet uses SI units, or meters, kilograms, seconds. So when you look at that log file, you can see exactly what values your VPLanet simulation is using, which can help you debug your input files. The section option here sets the output precision to be between 0 and 16 numbers after the decimal place. All right, the next group of options are related to integrations. You can instruct VPLanet to perform either a forward or a backward integration in time. So in this case, it's a forward integration, but you can use the option BDoBackward if you'd like to perform a backwards integration. The next line tells VPLanet that it should perform the integration using variable time stepping, which we highly recommend. With variable time stepping, the time step is chosen by the fastest varying parameter in the simulation. Well, you can use a fixed time step. That choice is more likely to result in a slower and less accurate simulation. but it can be helpful to use fixed time step when testing purposes. The next line is data, which is a coefficient that multiplies the time step and is basically your free parameter for optimizing the simulation in terms of accuracy and speed. A smaller data means that the code will be more accurate, but the integration will be slower. Moving on, d-stop time is the length of the time the simulation will run for, 4.6 billion years in this case. There aren't any units here, but remember that we set s-unit time to years. And last is the output interval, which is set to 1 million years. Finally, I want to note that time integrations are not required. If these parameters were omitted, VPLanet would still write a log file, if selected, and that file would contain all the output parameters predicted by your options. Okay, let's move on now to an example body file. In this case, we'll look at Venus's input file. Each body must have a unique name, which is set by the sname option. And then, of course, you also need to have a list of all the modules that VPLanet should apply to this body. And this is, of course, the key feature of VPLanet, so you need to include this line in order to actually perform a simulation. Next up are the options that describe the body itself. Our hope is that option names are self-explanatory. You might not agree or disagree with that description, but in most cases you can probably know what the output represents by looking at its name. But of course, you can always look at the online documentation, or you can run VPLanet with one of the -h flags to look at the onboard help. Note that in this case, some of the arguments seem to have unphysical values, like negative mass. Actually, what's happening here is that VPLanet is set up so that if you add a negative sign to a parameter that is positive definite, that overrides the units that were specified from the s-unit options. It forces what we call a custom unit. These custom units are generally typical for the Sun-Earth system. You can see in the comments that the different parameters have units that correspond to the Earth and to days, etc. As before, the custom units are documented online, and you can learn more about them with the help flags as well. Okay, the final option in this file is SA output order. This option is really important because it sets the list of all the outputs to write to the forward file. Every time the VPLanet reaches a time that requires an output, the code will write a line that contains the instantaneous values of the arguments you provide to this option. The order of the outputs is arbitrary, so you can mix them up however you want, but we do recommend including time because it's often really helpful to know the time step associated with a line of data. In contrast with the options, however, the arguments to SA output order do not need to be unique, and they are not case sensitive. In this case, we've used the full names of the outputs. Note that some of these outputs have negative signs. As before, these negative signs force custom units, and again, you can check the documentation to learn more about them. If no negative sign is prepended to an output, then the output units will be the same as those selected with the s-unit option. So, for example, if you were to output the mass of a planet and the output did not include a negative sign, the units would be whatever you specified for the arguments to the option s-unit mass. You can omit the SA output order option, and then no forward or backward file will be written. Note also that there are no lowercase prefixes as there were for the options. All outputs are written to the forward and backward files with double precision. All right, finally, I want to mention that the onboard help can also give you clues as to how you can modify a simulation and what outputs may be relevant to your simulation. For example, in this case, we've been discussing input files related to the atmospheric escape of water from Venus, which is driven by the XUV flux at the top of the planet's atmosphere. So maybe we're interested in outputting some properties related to the XUV flux, or maybe we want to know what other possibilities there are in terms of manipulating the XUV luminosity of the sun in the simulation so we can explore all the possibilities that VPLanet can simulate. If you run VPLanet -h pipe grep XUV, for example, then all the options and outputs that refer to XUV will be printed to your terminal. This command returns many lines from the onboard help, some of which are options and some are outputs. Remember that any of these results that start with a lowercase letter are options, while those that do not are outputs. All right, that concludes this introduction to the input files. Thanks for watching, everybody, and have fun simulating those habitable worlds.